Hi, and welcome to Dr. V's Chemistry webcast. Today, we're starting with equilibrium. What I'd like to do in this webcast today is to introduce the idea of reversible processes, and from there, get into a discussion of dynamic equilibrium, which actually is a very common and very important chemistry concept. And from there, I want to teach you how to write and evaluate equilibrium constants, which is a way of describing equilibrium situations. So, I want to start by introducing the idea of reversible reactions, but to do that, I need to step backwards. When we did our stoichiometry unit and when we talked about types of chemical reactions, we talked about reactions going to completion or going to an end, where the reactants make products, and that's the whole story. Reactions where this happens, where this is important, may involve forming a precipitate or forming a gas or forming water, where these are the driving forces that really make those reactants turn into products, and that's essentially what's happening. All right, so if we look at the reaction that I've got here, we've got a solution of sodium chloride being combined with a solution of silver nitrate. We've got this double displacement reaction occurring. We form aqueous sodium nitrate and solid sodium chloride. The formation of this precipitate, the silver chloride, really pulls this reaction in the forward direction. The reactants make products, and that's the whole description of the situation. But there are a lot of processes that are reversible, where they can be returned to their original state, where the forward and the backwards processes are occurring. So these happen all the time around us. So you can melt ice and refreeze the water. We can recharge the batteries for our laptops and our phones. So there are a lot of situations where this can happen. And we need to be able to talk about this because in chemistry, it turns out these ideas are really important. So when we want to write a reversible process, we use a double-headed arrow. Instead of a forward arrow showing it going in the forward direction, we use a double-headed arrow to show this. So in my dad's iced tea, he always puts way too much sugar in his iced tea. We've got two processes occurring. We have solid sugar going into solution. That's the forward reaction as I wrote it. But then any sugar that's in solution can also come and redeposit as the solid. That would be the reverse reaction. So when we put them together, we write that double-headed arrow to represent this. And in many situations, both forward and reverse processes can occur at the same time. And in fact, when equilibrium is involved, they are both occurring simultaneously and they don't stop. This becomes a difficult idea. So when they reach this balance point, all right, we call this dynamic equilibrium. Dynamic because it keeps going. But equilibrium because we're not seeing changes on a big scale, all right? At equilibrium, the definition of equilibrium is that the rate of the forward reaction equals the rate of the reverse reaction. That's really the definition here. So the forward process is happening at some rate, the reverse process is happening at the same rate. The net effect is that both reactions continue, but on a macroscopic change, on a macroscopic scale, we're not seeing changes. We don't see changes in concentration. We don't see changes in color. If we think about my dad's iced tea, right? Once as much sugar is dissolved as it's going to, and the forward process is occurring and the reverse process is occurring, the sweetness of the tea doesn't change, right? And so no observable macroscopic changes are occurring. Now, that doesn't mean that particles aren't changing, right? Sugar molecules are going into solution and other sugar molecules are coming out of solution. But on a macroscopic scale, we don't know which ones. We sort of know overall how many are solids and how many are in solution. So we can think about this graphically, which sometimes clarifies things. All right. So if we have a plot here of concentration versus time for A, B, and C, right, what we see is that they all started at whatever initial concentrations they started at, and the slopes of the lines change with time. All right, they start off fairly steep, they get shallower, eventually they level off. All right, what we can see here is that A and B are both reactants. Their concentration drops with time, and C is a product. Its concentration is increasing with time. All right, and then eventually they stop changing. Those concentrations stop changing because they've reached equilibrium. All right, and so graphically, once we see this plateau, we know that we've reached equilibrium. The reactions haven't stopped, but we're not seeing a change in concentration for A, B, or C. Right? One thing to note about equilibrium is the concentrations of the reactants and products do not have to be equal at equilibrium. The rates of the forward and reverse reactions are equal at equilibrium. We just need the concentrations to not change anymore with time. All right. And so this is a common thing that students struggle with. Right? The reaction rates are equal at equilibrium, but clearly the concentrations of A and B and C are not the same. They can be equal, but they're not required to be equal. Right? And then this ratio of products to reactants isn't going to change. We can actually think about this as a way of monitoring the reaction. Once we've established equilibrium, right, if the concentrations of A and B and C are changing, their ratios aren't going to change either. Right? And this ratio is called the equilibrium constant, or KEQ. Notice that it's a capital letter K, and then the EQ for equilibrium. There are actually different kinds of equilibrium constants, but we're just going to focus on the big picture right now. All right. In a very broad way, we can say that the equilibrium constant is the ratio of the concentration of the products over the concentration of the reactants. Okay. And this gives us a lot of information actually about what we have at that equilibrium position once we've established equilibrium. All right. We use square brackets to indicate molar concentrations. And when we report it as a dimensionless ratio. So we're not going to have any units for a KEQ, just a number. So the equilibrium constant really is very important, all right? If it ends up being a number greater than 1, there are more products than reactants at equilibrium. We might say that products are favored. If the equilibrium constant is less than 1, there are more reactants than products present at equilibrium. The reactants are favored. So if KEQ is less than 1, it's because my denominator is larger than my numerator in my KEQ expression. All right, so if we look at our graph again, right, at equilibrium, the concentrations of A and B, once they level off, are definitely higher than what I see for the concentration of C, right? And that would tell us that the KEQ is less than 1. I have more reactants than products at my equilibrium position. There are actually different kinds of equilibrium situations. We can have phase equilibria with a solid and a liquid. We can have solution equilibrium where we're maybe dissolving a solid in a solute, like the sugar example that I was talking about. This might also work with those slightly soluble salts. We can also have chemical reactions that establish equilibrium. But in terms of the idea of dynamic equilibrium, both forward and reverse processes are occurring. And for all of these, we can write a KEQ expression to help us talk about what we have more of at the equilibrium position. All right, a little chemistry humor never hurts either. All right, so now what I want to do is start talking about how to write equilibrium constants. And we do this by using what's called the law of mass action. I don't have to go into all the detail of where this came from. I want to just tell you how to use this. All right, how do we write KEQ expressions? Well, the first thing you always need is a balanced equation. And if you don't have that, then that's what you need to write. When we write these KEQ expressions, we ignore solids and pure liquids. Why? Well, KEQs are all about concentrations, and the concentration of a pure solid won't change, and the concentration of a pure liquid wouldn't change, so we don't put them into these expressions. We put our products in the numerator, and if we have more than one, we multiply them together. The other thing that comes out of the law of mass action is that the coefficients in the balanced equation become the exponents in the KEQ expression. Similarly, in the denominator, we put all the reactants. If there's more than one, we multiply them together, and the coefficients of the reactants from the balanced equation become the exponents in the KEQ expression. So if you know what these rules are, KEQ expressions are really pretty straightforward to write. So let's do some. All right. As a general expression, right, A and B react to make C and D. C and D are my products. They're going to go in the numerator. A and B are my reactants. They're going to go in the denominator. And then the coefficients, which here are lowercase letters A, B, C, and D, become exponents. All right, so here's a very general expression. But once you know how to do it, they go pretty smoothly. So we're going to do a couple of examples together. So here's our first reaction. 2 molecules of SO2 gas react with oxygen molecules to make 2 molecules of sulfur trioxide gas. All right, our product is SO3. It's got a coefficient of 2. We have 2 reactants, sulfur dioxide with a coefficient of 2, an oxygen gas with a coefficient of 1. So products over reactants, coefficients become exponents. Here's our KEQ expression, right? Sulfur trioxide squared in my numerator, SO2 squared times O2 in my denominator. Notice I got the square brackets because I'm indicating molar concentrations. Okay, let's do another problem with this. So now that we've got our KEQ expression, let's evaluate it. If at equilibrium, the sulfur dioxide concentration is 1.2 molar, the oxygen concentration was 0.35 molar, and the sulfur trioxide concentration was 0.85 molar, we can substitute these values into the KEQ expression and then use that to evaluate KEQ. I get a KEQ here of 1.4. Notice that I had 2 sig figs in all my concentrations, and therefore I report 2 sig figs in my KEQ, and I treat it as a dimensionless ratio, so there aren't any units here. So what this tells us is that at the equilibrium position, I've got a little bit more product than I do for reactants overall. All right, let's do another example. Magnesium metal can react with oxygen gas to form magnesium oxide. All right, so again, products over reactants, coefficients become exponents. But we also talked about the fact that we ignore pure solids and pure liquids. One of our reactants is a solid, and our product is a solid. So how do we handle those? Well, basically you put in 1 for those. So when we go to write our KEQ, the only species left to go into the KEQ expression is the oxygen. So, and our product is a solid. So the KEQ expression is 1 over O2. We leave our solids out of the expression. In terms of evaluating this, all right, if the oxygen gas molarity was 0.882 molar, we can substitute that into our KEQ expression, and we get a KEQ of 1.13. All right, so this gives you a good idea of how we can write KEQ expressions and how we can evaluate them. A twist on this, I could give you the KEQ in all but 1 concentration and have you solve for the missing piece and use your algebra skills. All right, but it all comes from this. Each reaction has its own characteristic KEQ value, but it is dependent on temperature. The initial concentrations, the equilibrium concentrations don't affect the value of the KEQ for that particular reaction. Only temperature will change the KEQ value. And we can start at a lot of different initial positions and wind up with the same value for the KEQ. It is a constant as long as you don't change the temperature, right? And as I mentioned before, we don't report units with our KEQ. We treat it as if it's dimensionless. And we also report them as decimals, and we do use sig figs when we report that, just to remind you of that. All right, so as a summary, all right, many reactions establish a dynamic equilibrium where the forward and reverse reactions continue, but we don't see any macroscopic changes in concentration. All right, the equilibrium constant describes the equilibrium position. Do we have more products or reactants at equilibrium? We can write equilibrium constants because we have some simple rules we can follow. And if we have equilibrium concentrations, we can use that to calculate values for equilibrium constants. That's great and a really good stopping point. Talk to you soon.